Good morning to everyone present here. It gives me a great pleasure to welcome you all to this guest lecture on multiple integrals. On behalf of Dharmanaidu Education and Charitable Trust, Board of Trustees, I take the privilege to welcome everyone. I cordially welcome our honorable chief guest, Dr. S. Dhanashekhar, Assistant Professor, School of Advanced Sciences, Vellore Institute of Technology, Chennai campus. I sincerely welcome our respected Secretary, Sri D. Dasarathan. I wholeheartedly welcome our Reverend Correspondent, Sri S. Amarnath. I extend my sincere welcome to our respected Director, Sri D. Sabarinath. I extend our warm welcome to our beloved Principal, Dr. S. Ramachandran. I cheerfully welcome our Vice Principal, Dr. Ahmed Mudasar Ali. I express my hearty welcome to our dear Head of the Department of Humanities and Science, Dr. R. Ariharasudan. I warmly welcome the Senior Professor of our Maths Department, Dr. V. Madhusudanan. I sincerely welcome all the faculty members and students to the occasion. I welcome one and all present here. I feel pleasure to introduce our chief guest, Dr. S. Dhanashekhar, Assistant Professor, Vellore Institute of Technology, Chennai campus. He received his BSc degree in mathematics in Sir Tyagaraya College, Chennai, University of Madras, in the year 1996. He received his MSc and MPhil degree in mathematics in Pachepas College, Chennai, University of Madras, in 1998 and 1999. He completed his PhD degree in mathematics in Bharathiar University, Coimbatore. His title of research in PhD is Contributions to the Study of Fuzzy Models in Optimization Problem. He published nearly 37 international journals. He also published two book chapters, namely Recent Advances in Control Problems of Dynamical Systems and Networks and Operations Research. He also published a patent titled Evaluation of Deep Learning Models to Classify Diabetic Retinopathy in Healthcare in October 16, 2020. His areas of interest in research is fuzzy optimization, network problems, page ranking optimization, and wavelet theory. His areas of interest in teaching is engineering mathematics, statistical models, numerical techniques, dynamics, and operations research. He has a vast experience over 23 years in repeated institutions from 1999 and presently working at Vellore Institute of Technology, Chennai campus. He has given many invited talks in various arts and science college, engineering college, and in other universities. He organized many workshops and seminars on various research tools. He also has held various major admin and academic responsibilities. Sir, I welcome you to share your knowledge to students.
Thank you, ma'am. Thank you for your nice introduction. And first of all, I thank the management and HOD of Mathematics Department, HOD of Mathematics Department, for giving me this opportunity to discuss multiple integral among them. Okay, so first of all, I get into the business because its time is 10:44. It's already. So, 1 minute, I will just change this. Ma'am, will it be like this? Shall I go on?
Okay, sir. Pakka, sir.
Okay. Okay. Right. So, multiple integrals. So, this is your unit 5. That's what right they told. This multiple integrals consist of evaluating double integral and triple integral. So we are not going beyond triple integral. We are just going to see what is double integral and what are all the theory behind the double integral and how to evaluate double integral. Then, if time permits, we will go for many things. That is, we will convert how the Cartesian coordinates into polar coordinates and when it comes to triple integral, how to convert a Cartesian coordinates into spherical polar coordinates and cylindrical polar coordinates. What are those things and how they help us to evaluate the multiple integral, double integral and triple integral easily. That's what the thing is, right? So this is what this whole thing is there. Now in this multiple integral, okay, let's go to the next slide. 1 minute, I'll go there. So the next slide will be okay. So review of first integral, that is single integral. That is a very important part we should remember, because when I go to double integral, if I don't know the basic concept of single integral, it will be a problem for me. So definite integral a to b f of x dx is nothing but it's a limiting of a series sequence, right? Or summation of things. That's what the thing is. Limit n tends to infinity. Summation I equal to 1 to n f of xi star into del x. That is, you will divide each and every curve or area where you are going to work into a small rectangle, small like this stripes. It can be called stripes. So their width will be always del x, and this f of xi is you are going to take any one point, sample point in this one, that can be called x1. If I take any point here, that can be called x2, like that. So I will apply it on this curve function y equal to f of x. Then after finding out this summation, I'm going to take limit n tends to infinity. What does it mean? That I will go on to increase these small rectangles, right, into infinite time, infinitely. Then this will be approximated to my single integral. This will be approximated to my single integral. Later at the end of this session, if time permits, I will show you in MATLAB how this is going on to happen. So this is your definite integral. So in a single integral, you are dividing the space where you are going to find it out by a small stripes, right? That is, here you are finding out the area of it. Now let's come to the double integral. So when you are coming to the double integral, volumes and double integral, okay, the main thing we have to be very careful about it. This is what we are going to know about. That is, you are going to divide the space into two lines. One is parallel to x-axis, another one is parallel to y-axis. That means this whole section will be divided into small rectangles like this. Small rectangle like this, whose width is del x and whose height is del y. Okay, del x and del y. Now if you see it in the figure, it will be like this. If I want to find out a double integral of this surface, I will come to later what is double integral. What you are doing is you are dividing this into like this two-dimensional figure like this. So you are dividing this area by small rectangles like this. Okay, when you are projecting it, it will be in the xy plane like this. XY plane like this. Then the double integral formula will be equal to double integral over r f of x comma y dA will be always equal to, now you are actually dividing it by two lines, isn't it? M and N, parallel to x-axis, parallel to y-axis, M and N. Therefore, it will be of double sum. Summation I equal to 1 to n, 1 to m, summation j equal to 1 to n, f of xi j star comma yi j star into delta e. And this will be when I take my m comma n tends to infinity. Then it will become approximated to a double integral. Now in double integral, what we are finding it out, that is a very important part we have to remember always. We are going to find out the volume of the solid. You are going to find out the volume of the solid under the surface z and above the xy plane. That is the very important observation we have to make. So when you are using the double integral, you are finding the volume of the solid, which is obtained by below the surface at equal to f of x comma y and above the xy plane. That is what we are finding it out in double integral. That's what double integral is all about. Now I hope right you understand this. To understand the double integral, we are taking one z surface 16 minus x square minus 2y square under a rectangle 0 comma 2 to 0 comma 2. So it is a square, not a rectangle. It is a square. Now the volume of this, you are just dividing the surface into four squares with the point 0, 1, 1, 2, 2, 2. Then you will apply this summation to get the result. But this result will not be equal to the double integral. This result will not be equal to the double integral. So you are dividing into four things. Therefore, summation I equal to 1 to 2, summation j equal to 1 to 2. See here, if you see that parallel to x-axis you have two lines, parallel to y-axis you have two lines. That's what given here. I equal to 1 to 2, j equal to 1 to 2, f of xi comma yj into delta a. Now what is the area of this square? The area, the sides of the square will be 1. That means the area of the square will be 1. Okay. So delta A. Now f of in this square, I'm going to take the right hand corner 1 comma 1, 2 comma 1, 2 comma 2, 1 comma 2. I can take any point in this rectangle, no issues for me. But I'm going to have a uniformity that I will take the right hand corner 1 comma 1, 2 comma 1, 2 comma 2, 1 comma 2. So for the first rectangle, I'm applying 1 comma 1. For the second rectangle, I'm applying 1 comma 2. For the third rectangle, I'm applying 2 comma 1. For the fourth rectangle, I'm going to apply 2 comma 2. Your delta A is 1. What is f of x comma y? This is, so you apply this point here. 16 minus 1 minus 2. So you will get 13 plus 7 plus 10 plus 4, 34. But this is not equal to your double integral. If you see it in the software, so you are dividing this into four squares like this. This is your surface. Now, if I increase it into m equal to n equal to 4, then volume goes to 41.5. When I increase it m equal to n equal to 8, right, my v equal to 44.875. Then my if I increase m equal to n equal to 16, my volume will be increased to 46.46875. Okay, so when I'm increasing my this m and n value, right, it goes on to approximate into a double integral. That's a key we have to remember in the double integral. Again, I'm telling you, right, to understand the purpose, right, you are finding out the volume of the surface and volume of the solid which was generated under the surface that equal to f of x comma y above the xy plane. That's what we are going to find it out. Now, let's go to the how to do the double integral. That's a very important thing we have to remember whenever we are going to have that, right? Now, 1 minute, I will just the double integral part. We have to have that. We will have many kind of things are there. That is, many kind of areas will be given to you, right? 1 minute, I will open my notebook. Forgot to open it, right? So will be coming in 2 minutes. Let's go get into the things. So I opened it. Okay, it's opening. Now, if you see that the iterated integrals, so this is called iterated integral. What is meant by iterated integral is double integral over r f of x comma y dA, where r is nothing but x lies between a to b, y lies between c to d. All are constants. If you see that all are constants, a to b, c to d, f of x comma y, dy dx. So when I go for that, right? So first, what I will do is I will integrate. I will integrate with respect to y first and apply the limit c comma d. That's what given. When I'm integrating with respect to y, I have to take my x as constant. That is a very important thing you have to remember. It's like partial differentiation. You are doing it, right? Let's see whether I can write it in this PDF so that, okay, we can have that because it will be easy for us to think. Right now, okay, I will go for it. 1 minute. Can I write like that? Where I should insert. Okay. don't have any option for annotation. Okay, leave it. Now, this is what the thing is. What I will do is, first I will take this integral f of x comma y dy. So I will integrate with respect to y and put the limit c to d. Then that result will be integrated with respect to x and put the interval a to b. Or I can do the vice versa. That is, first I will integrate with respect to x. Second, I will integrate with respect to y. With respect to y. Now, 1 minute. I control alt tab. So unsaved document. Is it this screen is visible, ma'am? Can we able to see this screen? Ma'am, I opened one notebook. Can you able to see it? Ma'am, are you there? Ma'am,
Sir, we can see only the PPT, sir.
okay. Right. So first, what I will do with this is what iterated integral is. When I'm integrating with respect to x, I have to take my y as constant. When I'm integrating with respect to y, I have to take my x as a constant. Always remember that dy dx and dx dy. Dy dx is vertical stripes. You have to draw a vertical stripes to find out the limits. And when you go for dx dy, always remember that it's an horizontal stripe. Now, if I take this example to solve it, double integral over r x minus 3y square into dA, where r lies between 0 to 2 and y lies between 1 to 2. So I can straight away put it, because since it's in constants, I can straight away put the limit. That is not a problem for me. So integral over 0 to t, integral over 1 to t, x minus 3y square into dy dx, x square, x minus 3y square into dy dx. This is given here. Given here. So then when I first integrating with respect to y, I will keep x as constant. Therefore, see that xy minus 3y cube by 3 will get cancelled. You will get this. Then this result will be integrated with respect to x and put the limits. You are getting minus 12. Same thing I can do it in the next one. First, I will integrate with respect to x, then I will integrate with respect to y. In both the cases, I'm getting the same result. So it is not like that, right? You have to have only one way. You have two ways, but you have to remember that when your limits are constants, then I can interchange like this. But when my limits are not constant, then it is very difficult to change. Right? This is in the MATLAB, right? This is the volume of the solid, you are finding it out. Okay. Now, again, another example is there, y into sine of xy dA, where the rectangle is 1 comma 2 to 0 comma pi. If you see that, right, this is nothing but the thing will be like this. So this is the volume, you are finding it out. You are getting 0 because the positive part and negative part will get cancel each other. So you may ask why that volume can be 0. Volume can be 0 because the positive in the positive volume and negative volume, it cancels each other. That's why this figure, if you see that figure, you will understand it. See that this is the volume, one volume plus this volume. Both the volumes gets cancel each other. That's why if you see that, you are getting 0 here. Okay, so you are going to do it in the same way. First, you are integrating with respect to x, apply the limits. Then integrating with respect to y, apply the limits. Okay. Now the problem arises when your x and y are in the functions, in the limit. So I have a region. In this region, see that y will be in terms of x and x will be constant. Then I have to go for dy dx. Then I have to go for dy dx. Now see that vertical stripes is there. Vertical stripes is there. And how will you find out the limits of this thing is, now double integral, you have to write down the double integral. Back to this pen. So, there anyway, design. Right. Now if it comes to here, now double integral, now I have to first down find out the inner integral limit. Now when I go for inner integral limit y, so I have to draw a vertical line. So where the vertical line starts, it starts at g1x curve and it ends at g2x curve. Therefore, my inner limit is g1 of x to g2 of x. At that time, my x varies from a to b. My x varies from a to b. This is how you have to find out the limits. So whenever a multiple integral problem comes double integral, if you know how to draw the surface or how to sketch the region, then it will be easy for us to understand the things. Otherwise, it will be a little bit difficult. So you have to understand it. Whenever we go for dy dx, you have to draw a vertical line in that region where you are going to integrate. Find out the inner limit first, then take the x limit as second. So it is dy dx. When it comes to uh, dx dy, I have to draw an horizontal line here. Now, if I draw a horizontal line here, it starts at this curve h1 of y, ends at this curve h2 of y. Therefore, my inner integral, if you see that, h1 of y to h2 of y, right? And at that time, my y varies from c to d. This is how you need to find out the limits of it. This is a very important task in this multiple integral. If you know how to find out the limit of it, this will help you in your vector calculus also, right? In your triple integral also, this will help us to do. So whenever, please remember that dy dx means you are going to draw a vertical line, find out the inner integral, right? And whenever we go for dx dy, you are going to draw an horizontal line, find out the limits of the inner integral. Now first example is given here, double integral over d x plus 2y into dA, where D is the region bounded by the parabola y equal to 2x square, y equal to 1 plus x square, y equal to 2x square and y equal to 1 plus x square. Now if I sketch the region looks like this. So the lower parabola is y equal to 2x square and the upper parabola is y equal to 1 plus x square. So you should know how to sketch this region. Just apply the points and then draw it. Now, if I want to go for dy dx, if I want to go for dy dx, I have to draw a vertical line in this region. In the region in between this two curve is the region where you are going to integrate. So therefore, when I draw a vertical line, it starts at the curve y equal to 2x square and ends at the curve y equal to 1 plus x square. At that time, your x varies from -1 to +1, -1 to +1. So this is what given here, -1 to +1, 2x square to 1 plus x square, x plus 2y into dy dx, dy dx. First, you have to integrate with respect to y, then you have to integrate with respect to x, right? Now let's go to the next example. In this example, find the volume of the solid that lies under the paraboloid z equal to x square plus y square and above the region capital T in the xy plane, bounded by the line y equal to 2x and y equal to x square. Now, if you draw the surface is like this, y equal to 2, y equal to x square and y equal to 2x line. If I draw the region, sketch the region looks like this, y equal to x square and y equal to 2x. Now, if I know the region this, right, now if I go for dy dx, what I have to draw? I have to draw a vertical line. So when I draw the vertical line, it starts at x square, ends at 2x. At that time, my x varies from 0 to 2. So this is for dy dx. When I come to dx dy, I have to draw an horizontal line. I have to draw an horizontal line. So if I draw an horizontal line, if you see that here, it starts at this curve, ends at this curve. So my x is equal to 1 by 2y, x is equal to root x. At that time, my y varies from 0 to 4. That's what given in this one. 0 to 4, 1 by 2y into root y, x square plus y square. You see that, right? 0 to 2, x square to 2x. So you should know how to find out the limits of the inner integral and the outer integral. That will gives you a great advantage of solving this. Great advantage of solving this part. 1 minute. Okay, solving this thing. Now next we go for how to solve this using polar coordinates, because polar coordinates are very important thing in this double integral part. It actually, right, it gives you a little bit advantage of solving this. Okay, solving the given thing. Now, I hope you don't have any doubts in this, right? In this one, see here also. So this problem, when I go for this problem, find the volume of the tetrahedron bounded by the planes x plus 2y plus z equal to 2, x is equal to 2y, x is equal to 0, and z equal to 0. I will write down this equation as z equal to, right, 2 minus x minus 2y. Okay, right? And if I put z equal to 0, this will become x plus 2y equal to 2. So I have x plus 2y equal to 2, x is equal to 2y, x is equal to 0, z equal to 2. So if I draw that, the figure will looks like this. Okay, the figure will be like this. This is x plus 2y equal to 2 line. This is y equal to x by 2 line. So in this region only you are going to evaluate the volume. Right? Now, if I go for dy dx, I have to draw a vertical line. So it starts at this curve, ends at this line. So y equal to x by 2 y, x by 2, y equal to 1 minus x by 2. At that time, my x varies from 0 to 1. 0 to 1. Okay. So this is how you can find out the limit of the given code. Right? Same thing. Whenever the region is not given, the limits is given. See that here in this integral, if you see it, it is nothing but x to 1. Y limit is x to 1. That means y equal to x and y equal to 1. So if I draw y equal to x and y equal to 1, this is y equal to x line, this is y equal to 1 line. So if I go for dy dx, right, if I draw a vertical line, it starts at x and ends at 1. Actually, it coincides with this. Now, if I want to change this into dx dy, then what I have to do, I have to just draw a horizontal line where the horizontal line starts at y-axis, ends at x is equal to y. That means my inner limit will be 0 to y. My inner integral limit will be 0 to y. So at that time, my y varies from 0 to 1. Okay. Now let's go to so these are all some of the example, you can work on it. Okay. Now let's go to the uh, properties of double integral or not needed. Triangular region. So we have many things to do. So now, if sometime, right, if you see that the things, find the area of the region enclosed by the parabola y equal to x square and the line y equal to x plus 2. Find the area of the region R enclosed by the parabola y equal to x square. Am I there? Yes. Okay. Right. Y equal to x square and the line y equal to x plus 2. Now, if I draw the figure y equal to x square, it's a parabola. Y equal to x square, it's a parabola. If I draw y equal to x plus 2, this is the line. Y equal to x plus 2 line, y equal to x square. Now, if I want to find out dy dx, then for me it's no problem, because you will have only one integral. Why it is you will have only one integral? Wherever I draw a vertical line, I will get the same thing. It starts at this curve, ends at this curve, right? But when it comes to horizontal line, when I draw horizontal line here, It starts at this negative part of this curve and positive part of this curve. But when I draw a horizontal line here, it starts at this line and ends at this curve. So it changes, right? That means when I go for dx dy, I should have two integrals, addition of two integrals. But when I go for dy dx, I can have only one. That's not a problem. That is what given in this one. Okay, now, all right, I will just minimize this. If you see it here, if I go for dx dy, I have two integrals. I have two integrals. See that here, this is from up to this you will have one integral. From this you have another integral. So when I draw it, it starts at the negative part of this parabola and positive part of this parabola. So this parabola is y equal to x square. That means x is equal to plus or minus root y. So it starts at minus root y, ends at plus root y, ends at plus root y. That is what given here, minus root y to plus root y. At that time, your y varies from 0 to 1. This is 1. So y varies from 0 to 1, x varies from minus root y to plus root y. Now when it comes to this place, right? So it draws at here. That means x is equal to y minus 2 and y equal to root y, because since it's in first quadrant, it's positive. So y minus 2 to root y. At that time, my y varies from this point is 1 and this point is 4. So 1 to 4. So you have addition of this two things are there, right? That's why. So for this problem, right, if I go for dy dx, I will have only one integral. If I go for dx dy, I will have I will have to evaluate two integrals. I will have to evaluate two integrals. Okay. Now let's go to the average. This is not needed for you, I hope. Now let's come to the double integral in polar coordinates. So double integral in polar coordinates is, now what you are going to do is we are going to change this point. Let's take this point as xy. You are going to change it into r comma theta, where x can be written as r cos theta, y can be written as r sin theta. So this is in physics, you will know that. When I have a vector, that vector can be not physics, mathematical also. It can be divided into two rectangular components. One is x cos theta, another one is sin theta. Same thing here. So if it is magnitude is r, your x will be r cos theta, your y will be r sin theta. Right? Now when I want to apply this polar coordinates in our double integral part, then we have to be very careful, because whenever you are changing dA in polar coordinates, you have to apply r into dr into d theta. That's a key you have to remember. So when you are changing x to r cos theta and y to r sin theta, then you have to change your dA as r into dr into d theta. Why it is? Where r is nothing but it's a Jacobian part. It's a Jacobian part. Whenever you are doing a transformation from one coordinates to another coordinates, the Jacobian should not be zero. That is the important property we have to remember in mathematical thing. So this R is nothing but Jacobian. If you studied Jacobian, you can find out the Jacobian of Cartesian to polar is R. So you are multiplying that by R. Or geometrically, you can have this. This is r theta, this is dA. So r theta into dr. So the whole dA can be written as r into dr into d theta. So it's a sector. It's called a, right? Now please remember that whenever you are changing into polar coordinates dA or dx dy or dy dx, always you have to put r into dr into d theta. R into dr into d theta. That is the key we have to remember. Now let's take, these are all not needed for you. Now let's go to the changing into polar coordinates and do. Now evaluate this integral. Now when I go for evaluating this integral, this is very little bit difficult for me to evaluate. because it is 0 to root of 1 minus x square. So when I integrate this with respect to y, x square into y plus y cube by 3. When I apply in the place of y the limits, this limit root of 1 minus x square, it becomes complicated too. So when I want to simplify this, I can go for polar coordinates. I can go for polar coordinates. So when you can go for polar coordinates is when you have this kind of things are there. Now, for example, if I go for this, this is given as R semicircle. See that the limit is 0 to 1, and also you will have x square terms and all that. So we can change these things into polar coordinates. So what you are going to put is x is equal to r cos theta, y equal to r sin theta, and instead of d r into dr into dt. Square plus y square is nothing but okay r square cos square theta plus r square sin square theta. So r square into cos square theta plus sin square theta, it will be 1. Therefore, you will be left with r square into r into dr into d theta. Now, if I see this figure, it is 0 to 1, 0 to root of 1 minus x square. All are positive. That means it will be in the first quadrant. It will be in the first quadrant. Now, the first quadrant, if it is in the first quadrant, then what is your theta? Theta will be from 0 to pi by 2, isn't it? Theta will be from 0 to pi by 2. And what is the radius of that? It's a unit circle. It's a unit circle. I don't know how to share this notebook. If it is there, I will just write it down because I cannot able to write down in this thing. Okay, right. So if I go for it, y equal to 0, y equal to root of 1 minus x square. Now if I square the term, what I will get? I will get x square plus y square equal to 1. It's nothing but it's a unit circle. It's a unit circle taken in the first quadrant. Taken in the first quadrant. What is first quadrant? This is first quadrant. Now in this first quadrant, the angle is from 0 to pi by 2. So if I need to draw a line like this, radial line, it starts at 0, ends at this curve. So at this curve, my r is 1. Therefore, here I am putting 0 to 1, 0 to pi by 2, r square into r into dr into d theta. So we have to be very careful in this. We have to be very careful in this, right? Okay. So this is what the thing is. Now, if I come to the next one here, see that find the volume of the solid region generated by above bounded above by the paraboloid z equal to 9 minus x square minus y square and below by the unit circle in the xy plane. Below by the unit circle in the xy plane. Now, what is unit circle? Full circle. That means its r will be when I draw a radial line. When I draw a radial line, it will be like this. If I have a full circle, if I draw a radial line, it will be from 0 to 1 because it's unit circle. So it is 0 to 1. So if it is full circle, what is the angle? The angle is 0 to 2 pi. So 0 to 2 pi, 0 to 1, 9 minus r square into r into dr into d theta. Okay, so this is how to do it. Now, how it is coming? Minus x square plus y square. This x square plus y square is nothing but r square. So instead of this dA, I'm going to apply r into dr into d theta. So this is how you can. This also you can just change it into polar coordinates and do it. Since it's 0 to infinity, 0 to infinity. That means it is in the first quadrant. It is in the first quadrant. All are positive. X is also positive. Y is also positive. So in the first quadrant, the angle is 0 to pi by 2. Now the radius of this circle it takes all the space in the first quadrant. That means it is from 0 to infinity, 0 to pi by 2. Then 1 by 1 plus, instead of this x square plus y square, you will apply r square. So 1 plus r square of whole square into dx dy. Okay, this is how you can convert a thing into polar coordinates. Same thing here. Okay, now let's go to the triple integral. Now when it goes for triple integral, now by using double integral, how will you find out the area is the same formula. In that, this f of x will be 1. Double integral over d, dA will give you the area. Double integral over d into dA. There won't be any f of x comma y. The f of x comma y will be 1. So that type of things is called area. When I want to find out area using double integral, right, see here, find the area of the double integral. So when I go for area of the double integral, there won't be any f of x comma y. Double integral over r or d, whatever region it is given, into dA. So when I'm going to change it into polar coordinates, instead of dA, I will apply r into dr into d theta. Now when it comes to triple integral, so this is my triple integral. So in the triple integral, what you are doing is you are dividing the region into cubes. That is for x parallel to x-axis, parallel to y-axis, parallel to z-axis. So the whole thing will be divided into cubes like this, whose volume is delta x into delta y into delta z. Delta x into delta y into delta z. So it is nothing but again, but you will have three summation, triple sum. Limit L comma M comma N tends to infinity. Summation I equal to 1 to L. Summation J equal to 1 to M. Summation K equal to 1 to M. Into del V. This will be approximated to triple integral. Okay. Now triple integral again. You may have a triple integral in a rectangular box. A to B, A, B, C, D, R, S. This is my x value, y value, z value. Right? So dx, dy, dz. It is like same thing. First integrate with respect to x, apply the limits, then integrate with respect to y, apply the limits, then integrate with respect to z, apply the limits. Okay. Now an example is given 0 to 1, minus 1 to 2, 0 to 3. So integration 0 to 1, integration minus 1 to 2, integration 0 to 3. Right? First I will integrate with respect to x first. So y z square will be constant. So it will be x square by 2. Apply the limit. Then integrate with respect to y. Apply the limits. Then integrate with respect to z. Apply the limits. Okay. Now in this also you will have functions. So my inner integral z will be in terms of xy. My inner integral y will be in terms of x. My outer integral x will be a constant. Integral a to b, integral g1 of x into g2 of x, integral u1 of x comma y into the u2 of x. So now an example is given, triple integral over E z into dv, where E is the solid tetrahedron. If you draw the solid tetrahedron, this will be the thing. Okay, right? And when I projecting this tetrahedron into xy plane, I will get a rectangle like this. I will get a rectangle like this. So my z limit starts from 0 to 1 minus x minus y. So my z limit starts from 0 to 1 minus x minus y. Okay. And when I want to find out x and y, then I have to go back to my double integral concept. I will just project this into xy plane. When I'm projecting into xy plane, it becomes a rectangle which bounded by the line y-axis, x-axis, and y equal to 1 minus x. How you are getting this? Put z equal to 0. So when I go for dy dx, I will draw a vertical line. So this vertical line starts at 0, ends at 1 minus x. Therefore, my y limit is 0 to 1 minus x. At that time, my x varies from 0 to 1. So if you see that integration 0 to 1 minus x minus y, integration 0 to 1 minus x, 0 to 1. This is how you can find out the limits of the triple integral. So in both the cases, we have to be very careful in doing those, finding out the finding out the limits, because which which plane you are going to projecting. That's a very important part you have to. For example, in this example, if you see that, evaluate triple integral over e root of x square plus z square into dv, where e is the region bounded by the paraboloid y equal to x square plus z square and the plane y equal to 4. That means y limit is already given to us. Y limit is already given to us. It is from x square plus z square to 4. If I draw that, it will be. That means I have to project this into xz plane. I have to project this into xz plane, not in the xy plane, because y limit is already there. So I will project this into xz plane. That means I have to put y equal to 0, isn't it? Right? That is what the thing. So we have to remember that. Very important. We have to remember that point, very important. Since y and z, y values limits are given, no need to project it into xy plane. Again, you will get a right. You won't get the result. So you have to project this into xz plane, and you have to get the things. Okay. Now, if I put it like that, I will get those things. Right. Okay. So we have to be very careful in this. See that when you are putting in the xz plane, what is the thing? Now, if I putting in the xz plane here, it is now x is at plane here, right? Now my y is 4, so I will apply 4 here. X square plus z square equal to 4. That means it's a circle center at origin with radius 2 in the xz plane. In the xz plane, x square plus z square equal to 4. So that's what given here, minus root of 4 minus x square. So when it is circle, it is easy to apply the polar coordinates. So I can easily find out the answer for it. So that's a key we have to remember it. Then the application of triple integrals, you can find the volume. Same thing like in area. Triple integral over E dV will give you the volume. Triple integral over E dV will give you the volume, right? Now, in this one, for example, the same kind of example we have here. Now, if you see here in this problem, x limit is given. So that means I have to project this plane into yz plane. That means this will become y square plus z square equal to 16. That means it's a circle center at origin with radius 4. Okay. Now, triple integral in cylindrical coordinates. What is meant by cylindrical coordinates? Cylindrical coordinates, it's a combination of polar and Cartesian. So here, if I have a point here, here in this point, 3-dimensional point. So this point can be obtained by using polar coordinates, and this point can be taken as a distance. So my cylindrical coordinates are nothing but x is equal to r cos theta, y equal to r sin theta, z equal to z, z equal to z. So when I'm changing a triple integral into cylindrical coordinates, then instead of that dv, instead of this dv, instead of this dv, I have to apply r into dz into dr into d theta. That is the key we have to remember here. See that instead of this dz, dy dx, if I'm going to replace this by cylindrical coordinates, when I can apply cylindrical coordinates is if my limits right coincide, if the region you are going to integrate a circle, then I can go for cylindrical polar coordinates in triple integral. So here, if you see here, instead of dv, we are going to apply r into dz into dr into d theta, where x square, x is equal to r cos theta, y equal to r sin theta. Therefore, x square plus y square equal to r square, r into dz into dr into d theta. This is the thing we have to remember here. Now, here in this case, The circle's radius is 2. Therefore, it is from, according to it, you need to find out the things. That is the key you have to remember in this cylindrical polar coordinates. Cylindrical polar coordinates. Now, where you can apply the cylindrical coordinates? Cylindrical coordinates are useful in problems that involves symmetry about an axis, and z axis is chosen to coincide with the axis of symmetry. If I have an axis here and it is symmetric about that axis, what is symmetric? This place and this side will be the same. Then you can apply cylindrical polar coordinates. Okay. Now we have another coordinates called spherical polar coordinates. Now spherical polar coordinates, I think they will take it in different way, but here it is in this book it is different because I think in your thing they will use R, but here they are using rho. So no need to worry about it. Both are same, but you have to remember where to apply the spherical polar coordinates. Now the spherical polar coordinates are useful where there is a symmetry about a point. Symmetric about a point. It is a symmetry about a point. Then you can apply spherical polar coordinates. Spherical polar coordinates. Okay, right? So this is what in your double and triple integral we have. Okay, so this whole unit is very easy when you practice many problem. The first and foremost thing is you should know how to sketch the region. That is the very important part you have to remember. Second thing is if it is dx dy, you have to draw an horizontal line to find out the inner limit of the inner integral. If it is dx dy, you have to draw a vertical stripe to find out the inner limit of the limit of the inner integral. So that is the one. When it goes to triple integral, according to it, you have to do. So I think that's what I have today. Uh, if you can interact with me, you can interact. Can anybody can interact or not? Ma'am, can they be interact with me or
You can
ma'am?
proceed, sir.
Yes, ma'am. Are they interact with me? They can able to interact with me or no?
Students, if you are having any doubts, means you can ask, ma. You can post your questions in the chat box, ma.
So that I can reply to it. And the whole content for this class, I'm taking it from Stewart Calculus. It's a book called Stewart Calculus. Now, if you want to understand the basic things about all these multivariable things and basic differentiation and integration, we have many books. Can I type it in the chat box? First book you can go for is Stewart Calculus. Stewart Calculus. It's actually available in the net to download. Just one book, Stewart Calculus, because in MIT they are using this book only. Master Institute of Technology. That's a number one institute in the technological thing. Then we have another book called Thomas Calculus. Thomas Calculus. So this book is also very elaborately. It will tell you how this happens. Okay. So since I didn't get into the more background here. So each and everything will be explained there in the right Stewart calculus and Thomas calculus. If you are interested in max and if you want to learn more things, then you can have this book so that it will help you. So any doubts you have? Any doubts? No doubts. Yes, ma'am. Shall we wind up, ma'am?
Sure, sir. One second, sir. So I'm handing over mic to Mr. Anvanathan, sir. He'll give you the vote of thanks.
So thank you, Dr. Dhanasega, sir, Assistant Professor from VIT Chennai campus, for nice explanation about multiple integral. Thank you, sir.
Thank you.
Good afternoon to one and all. I thank on behalf of our department, Humanity and Science, to respected Secretary, Sir Dr. D. Dasarath sir, Sri, and Honorable Correspondent Sri S. Amarnath sir, and our Correspondent Director Sri D. Sabarinath sir, helped to organize this guest lecture. And also I thank to our respected Principal, HOD, and other staff members who have made this event as a successful one. I also thanks once again our guest lecturer, Dr. S. Dhanasegar sir, for his wonderful speaks in multiple integrals. This is very helpful to our students, and also I thank our students for patient participation. Thank you, sir. Thank you.
Thank you. I thank
Thanks a lot, sir.
the yes, ma'am. I thank the management and the staffs for inviting me to give this lecture, and I thank Dr. Madhusudan because he is the one who contacted me. I think he is there or not. I don't know. Right? If it is not there, convey my thanks to him. I
Sure,
hope
sir.
right.
Sure.
I hope I actually right satisfied your needs. Right. Thank you. Thank you all.
Of course, sir. Of
Okay.
course.
Of course, you satisfied, sir.
Thank you. Thank you.
Thank you, sir.
Thank
Thank
you.
you, sir.
Thank you, sir.
Ma'am, shall I leave, ma'am?
Yes, ma'am.
Yes, sir. You can leave, sir.
Okay, ma'am.
Thank you.
Thank you.
Thank you.
Thank you,
Thank
sir.
you, sir.